Okay, so the quantum mechanical model of the atom replaced the Bohr model in the early 20th century. In the quantum mechanical model, Bohr's orbits are replaced with quantum mechanical orbitals, okay? And we will just refer to them as orbitals from this point on. And the other big thing is that electrons weren't only also we know that they have particle-like behavior, but turns out they also behave like waves, just like photons. So that was like a really big advancement in the field as well. So that's actually the heart of the quantum mechanical model theory, is that electrons, like light, behave as waves when traveling through space. This was first proposed by de Broglie in 1924 and was confirmed experimentally in 1927. The experiment that proved the wave nature of electrons is beyond the scope of this course, but you'll probably learn it in Chem 200. But long story short, this means that electrons behave as particles and as waves. Okay? And going back to the orbital situation, orbitals are different from orbits in that they represent probability maps. We'll talk about this in a second, that show a statistical distribution of where the electron is likely to be found. Okay, so orbits are now orbitals, okay? And orbitals are probability maps showing the statistical distribution of electrons, all right? The likelihood of where an electron is going to be found around an atom. Okay. So quantum mechanics revolutionized physics and chemistry because in the quantum mechanical model, electrons do not behave like particles flying around through space, they behave as waves. We cannot, in general, predict their exact paths. Okay, we can't see an electron. All right, I'm sure that you've heard this before, Heisenberg's uncertainty principle, and this is actually, I'm not going to really go into it. For more information, again, which is beyond the scope of this course, you can read about it, Heisenberg's uncertainty principle. Sorry, I have a dog and he barks a lot. But in Heisenberg's uncertainty principle, it states that if we know with accuracy the position of an electron, we cannot know its velocity. And you need to know position and velocity in order to predict the path of a moving object. This is the trajectory. So if we can't know both, we can't know its trajectory. So in quantum mechanics, trajectories of electrons are replaced by probability distribution maps. An orbital is a probability map, okay? This shows where the electron is likely to be found when the atom is probed. It does not represent the exact path that an electron takes as it travels through space, okay? So, let me just give you an example. Your book pulls this sports analogy, which I kind of like, and when we're trying to talk about probability maps. So let's think about, contrast the behavior of a baseball with that of an electron. Imagine that a baseball is thrown from the pitcher's mound to a catcher's mound at home plate. The baseball's path can easily be traced as it travels from the pitcher to the catcher, all right? The position and the velocity is known, so we can predict its trajectory. In the quantum mechanical world of the electron, the catcher could not know exactly where the electron will cross the plate for any given throw. He would have no way of putting his mitt in the right place to catch it. He has no idea where it's going to go. All right. However, if the catcher kept track of hundreds of electron throws, he could observe a reproducible statistical pattern where the electron crosses the plate. He could even draw maps in the strike zone showing the probability of an electron crossing a certain area. These maps are called probability maps. Okay? So to describe the behavior of a pitched electron, you would have to construct a probability map where it would cross home plate. Okay, so remember, the electron is the baseball, and long story short, what you can sit back and do is, through observation, many observations, you can create a probability density map of where the baseball crosses the plate. This is the same thing of electrons within orbitals. I'm sorry, yeah, orbitals. So in the quantum mechanical model, a number, all right, so this is really important. A number and a letter specify an orbital. Okay, just bear with me, and you should probably write this down. The lowest energy orbital is the in the quantum mechanical model is called the 1s orbital. All right, 1 being the number that's associated with it and the letter. So the 1s orbital. It is specified by the number 1 and the letter s. So the number 1 is called the principal quantum number. So before, from the Bohr model, we just had quantum numbers. Now we have principal quantum numbers that specify the energy of the orbital. Okay, it's called n, but it's a whole number 1 through 6. Okay, it is the principal shell of the orbital. Okay, so the orbitals have shapes. Okay, so here we go. The letter indicates the subshell, all right, of the orbital and specifies its shape. So you have a letter, all right, so you have the principal quantum number, which is a number, and then you have a letter associated with it that is called the subshell. The subshell indicates the orbitals within the subshell and the shape of the orbitals. The possible letters are S, P, D, and F, and each one has a different shape. Orbitals within the S subshell have a spherical shape. Okay, and so first of all, let's ask ourselves, well, why do S orbitals or an S subshell have spherical shapes? So right below here we have the dot. On the far left we have the dot representation of the 1s orbitals. Remember what a dot representation is. It's the probability density. So basically what you can take a look at is that or what you can tell from the probability density map is that the 1s orbital essentially takes a spherical shape. So basically what they do is they just take the probability density map and then they convert it into a 3D representation, and turns out it looks just like a sphere. Okay, and that is specific to the the s orbital, the s subshell, and the s orbital. Okay, so we already talked about s orbitals have spherical shapes and how the shapes come from the probability density map. Orbitals are also represented, all other orbitals are represented as different geometric shapes, and that encompasses most of the volume of where the electron is likely to be found. The greater the dot density, or the probability, near the middle represents a higher probability of finding the electron near the nucleus. So again, here's the 1s orbital right here, but look at p orbitals. So there's a p subshell, right? And just to let you know, within the p subshell, there are 3 p orbitals, and they do not look like spheres. They have this kind of dumbbell shape. And there are 3 of them because they align themselves along the axes. We'll talk about that a little bit later. But another example, here's a d orbital. Okay, d orbitals don't look like s orbitals. They don't look like p orbitals. They have this kind of clover shape. All right. And we get these geometric shapes from the probability densities. Okay, so each orbital is described by a number and a letter. The number is its principal quantum number, and that's associated with its energy level. And its subshell, which is described by a letter, S, P, D, or F. Principal quantum numbers indicate energy levels of the subshells and how many subshells are in it, essentially. Subshells indicate shapes of orbitals, and subshells also determine how many orbitals are within the subshell. So, S subshells have 1 s orbitals, p subshells have 3 p orbitals within them. D subshells have 5 d orbitals within them. And F subshells have 7 F orbitals within them. I know that this is kind of hard to imagine right now, but just bear with me, okay, and we'll get through it. Within each orbital, 2 electrons can be held, okay? So we have our principal quantum number, and within our principal quantum number, remember, our principal quantum number is an energy level, and within that energy level, we have certain subshells. And within those subshells, we have orbitals. And within the orbitals is where we actually find the electron. You with me? Okay. So we already said that a 1s orbital or an s orbital, basically every n equals 1 through 6 has s orbitals. But not every single n equals 1 through 6 has a p subshell. So each principal level, n equals 2 or greater, contain a p subshell. And within each p subshell, there are 3 p orbitals. Okay? And the p orbitals differ only in their 3D representation in space. And as you can see here on the slide, I have the px, py, and pz orbital, and they're all oriented along the x, y, and z axis, respectively. Okay. So in order to have a p orbital, you have to be in the n equals 2 energy level or greater. So you can technically have a 2p, a 3p, a 4p, a 5p, and a 6p orbital. D orbitals are a little bit different. They're shaped differently, but they're also found in certain energy levels. Specifically, they can only be found in n equals 3 or greater. So that means there are no 1d orbitals, or there's not a 1d subshell, and there are no 2d subshells. But there are 3d, 4d, 5d, and 6d. And like I said before, within each d subshell, there are 5d orbitals. They look like what you see on the slide here. And as you can see, it's 4 of the 5d orbitals have a clover leaf shape, while with 4 lobes of electron density around the nucleus. The dz squared is the only different looking one, and it has 2 lobes along the z-axis and a donut shape ring around the xy plane. I'm not going to show you the f orbitals because who cares? No, I'm just joking. But we're just going to focus on the sp and d orbital. So the number of subshells in a given principal shell is equal to the value of n. Okay, so what does that mean? All right, well, let me just take you through this. Okay, so like I said, you can have n equals 1 to n equals 6, but right here on the slide, I just have n equals 1 through 4. All right. So if you just look at the n equals 1, the number of subshells within the n equals 1 shell is 1. If you look above that, the number of subshells within the n equals 2 shell are 2. The number of subshells within the n equals 3 shell are 3. And the number of subshells within the n equals 4 are 4. So, what does that mean? Well, since n equals 1 can only have 1 subshell, that means n equals 1 only has an s subshell. N equals 2 can have 2 subshells, the S and the P. N equals 3 can have 3 subshells, S, P, and D. And N equals 4 can have 4 subshells, S, P, D, and F. Okay? And remember that within each subshell are a certain amount of orbitals. All S subshells have 1 s orbital. All p subshells have 3 p orbitals within them. All d have 5 d orbitals. And all f have 7. and within each orbital, 2 electrons can be held. It's also important to know that, just a reminder, that energy increases with the principal quantum number. So as we go from n equals 1 to n equals 4, n equals 4 has greater energy than 3, which has greater energy than 2, which has greater energy than 1. So again, the higher principal quantum number, the higher the energy of the orbital. Also, the more possibilities. Oh, sorry, excuse me. I'm just going to keep going. Since the 1s orbital has the lowest possible principal quantum number, it is in the lowest energy shell and has the lowest possible energy. And that's pretty straightforward. But I want you to bring this back to the whole Bohr model really fast with the orbits and the ladder and everything. This is still kind of the same concept, but instead of having just an orbit, right, we've expanded, the quantum mechanical model has expanded upon that, and now within each orbit or shell are all these subshells that contain orbitals. As we increase energy, we also increase size, okay? So a 1s orbital is smaller than a 2s orbital. A 1s orbital is also lower in energy than a 2s orbital. So as we increase the quantum number, the principal quantum number, these subshells also get bigger and they have more energy. And just in case you were wondering what it all looked like, okay, this is all of the orbitals of an atom, right? Basically, it looks like it's probably, hold on, let me take a look really fast. I forgot about this slide. This is for neon. Okay, we're assuming that all these orbitals are filled. You have a 1s orbital with 2 electrons, and then you go up a higher energy level to a 2s orbital. So now we're in the principal quantum number of 2. 2s orbital, that contains 2 electrons as well. And then because we're in the principal quantum number of 2, we can also have a p subshell. So that's where the 2p subshell comes in. And within the p subshell, there are 3 p orbitals, all right, along the axes. All right, those are the dumbbell shapes along the axes. And within each 2p orbital, you can have 2 electrons for a total of 6. So if we add these up, if these orbitals were filled with electrons, in the 1s orbital, you'd have 2 electrons. In the 2s orbital, you'd have 2 electrons, so for a total of 4. And then in the 2p subshell, you're going to have 3p orbitals, each with 2 electrons, so that's 6. So collectively, that's 10 electrons. And if you look at the periodic table and you find out which atom has 10 electrons, that would be neon. Okay, so what does this all look like together? I took the shapes out just so you could see everything. So just notice really fast that we have on the left side, we have energy. So as we start adding these subshells and these orbitals, we're increasing in energy, okay? So this is actually what rubidium looks like. This is the electron orbital, one of the electron orbital diagrams for rubidium, which has, it's number 37, all right, on the periodic table. So it would be really great if everybody could take a look at their periodic table really fast. Again, rubidium is number 37. Okay, so if you take a look, and if you can go ahead and pause it here to get out your periodic table, I think it's a really good idea to do that. But if you take a look at your periodic table, you're going to see rubidium number 37 is in what? It is in the 5th row. I'm sorry, fifth row of the periodic table. So I want you to keep that in mind, okay? So within the rubidium atom, we'll start off with, it has associated with it a 1s orbital, all right? That's the lowest energy one that contains 2 electrons. We move up to n equals 2, all right? principal quantum number n equals 2. Within the n equals 2 shell, we have two subshells. We have the 2s subshell that contains a 1s orbital, and we have a 2p subshell that contains 3p orbitals. Now remember, n equals 2 cannot have any d orbitals. So we've only put in 2, 4, 6, 8, 10 electrons, and we have 37 more to go. So where are they going to go? We're going to have to go up to n equals 3, right? So within the n equals 3 shell, we have 3 subshells. The 3s, the 3p, and the 3d, okay? Then we have to jump up and say, all right, n equals 4. So we have within the n equals 4, we have a 4s, a 4p, and a 4d. And finally, n equals 5. We only have one electron in that, and that's the 5s orbital. So we're going to jump in. I'm going to stop this lecture or this section of the lecture after this slide, but what I want you guys to also notice from this is that the energy levels are they're not stacked, they're staggered a little bit. And what I mean by that is, if you look at the 4s orbital, you can see that it's lower in energy than the 3d orbital. Okay? It's lower in energy than the 3d orbital. And the 3d orbital is lower in energy than the 4p orbital. Jump up to the 5s. The 5s orbital is lower in energy than the 4d, and the 4d orbital is lower in energy than the 5p. Jump up to the 6s. Now we're not filling electrons because we've already filled the 37 that's in there. But if we were to fill up all these orbitals with electrons, you notice the 6s orbital is lower in energy than the 4f, which is lower in energy than the 5d, which is lower in energy than the 6p. The 7s orbital is lower in energy than the 5f, which is lower in energy than the 6d, which is lower in energy than the 7p. And this type of ordering from the energy level perspective, that is how we're going to fill electrons and write out electron configurations. Okay? So the next section of slides that I'm going to upload, we're going to be covering electron configurations, and that's still going to be part of chapter 9.